half-life. Half-life is more of a nuclear decay kind of topic where we talk about, okay, if you have a radioactive isotope and it's decaying, how fast does it decay? How dangerous is it? Well, if it decays, if its half-life is 1 billion years, then we're not going to worry too much. Sorry. Because in the few minutes or few hours that we're exposed to it, I mean, we're talking about billions of years for it to decay any appreciable amount. That's not a big deal. But when we deal with reactions, we also can determine the half-life of reactions. Since we're talking about kinetics and how fast reactions are, the half-life is also, as well as the K value, an indication of how fast a reaction is going. So you see a definition up here, just like with radioactive decay, half-life is the time that it takes for half of a reactant to run out. We only use the integrated rate law for half-life because the integrated rate law has to do with time. The differential rate law, there's no time factor in there. It's rate versus concentration, the differential is. But the integrated rate law is concentration versus time. So yeah, anytime you deal with a half-life, you're going to be dealing with an integrated rate law. Did you hear that? Whenever a problem talks about half-life, you know you're going to deal with the integrated rate law. And this part that I highlighted is always true. What half-life means is that whatever your initial concentration was, if you cut it in half, that's what the current concentration is. So how long does it take for this to equal that? If you can do algebra, you can get through this just fine. Hi there. Oh.
I know.
No, you know what? Go ahead. You go ahead.
No.
I was going to say, can you wait until the end of the hour, but...
that's why I'm here.
Oh, perfect, yeah. That thing is ready to go whenever you want to re-image it. I don't have anything saved on the...
Okay, oh, that's what I wanted to ask.
Yep, yeah, because I talked to Bill,
Right.
and he said, hey, do you have anything saved on there?
Recording this?
No.
Why not cut that out? Why not record it, man?
So anyway,
I was gonna do it.
Perfect.
On the mustache.
What is it?
Get a closer.
Okay.
You're in trouble?
Yeah, she's in trouble, yeah.
She's playing the dunce suit.
Oh, so we're talking first order here, right? Most common order is first order.
That's what it is.
And we're dealing with the integrated rate law when we talk about half-life, yeah. So that means if it's first order, that means that, let's just write out the first order equation first. It's been a couple of days. Uh-oh, I did that wrong, didn't I?
Yeah.
What's wrong with it?
Ellen.
Yes, this term is natural log.
Initial, yeah. Come on, Mr. Moore.
You're paying attention. I accomplished my goal.
You meant to do that.
I did.
You're testing us.
This is the integrated rate law. If we're talking about the half-life, what the question is what is the time that it takes? So that's what we're going to solve for. The time that it takes for the concentration to be cut in half of what it was originally. So we can just do the algebra. This term right here can be replaced with 1/2 A0.
Yeah.
Yeah?
Yeah.
All right. So natural log of, and let's see, can I do this? A0 over 2?
Yeah.
Equals negative KT plus natural log of A0. All right, let's do the algebra and clean it up. What's this thing equal to? Would it be natural log of A0 minus natural log of 2?
Yeah.
Yes.
Yeah.
Man, I gotta go look at all.
I actually remember that. Yeah.
All right,
No, you
so the natural log of A0 minus the natural log of 2 equals negative KT plus natural log of A0. What do you see?
You can subtract the natural log of.
Yes, I want to get the natural log to A0 on one side, so I'll subtract it from this side, right? Uh-oh.
It gives you nothing
It's
left.
going to cancel out, isn't it?
That's okay. That's okay.
gone, gone.
All you need is time.
Yeah, so we're trying to solve for the time. The question is, how long does it take for the original concentration to get cut in half? So how long it takes is solving for the time. Can you solve this thing for time?
Yeah.
Yeah.
Time
Alright.
is equal to L.
Time is equal to
The natural log of 2.
negative natural log of 2 over negative k, or also known as natural log of 2 over k. This is how we find the half-life of a first order reaction. Sorry about my circle there.
Is it always going to be Ln2 over?
Yes. Now, that means that's a constant value. Ln2 is a constant. If I remember right, Ln2 is 0.693.
Whoa.
Just plug that number in. And that might be good to know if I had this on a
Please
a
don't.
choice test where you couldn't use a calculator.
Please don't.
0.693.
Please don't.
It's so mean.
So, yeah, if you know K, and you might, then you can find what the, you know how problems always say part B, find the rate unit, or the rate constant K. So you're probably gonna know K, and then, in a problem, and then they'll ask you for the half-life. This is just good for first order, though. See how you start with a natural log of business as first order. All right, Rithi, if it's okay with you, and the listening audience, can we, just fast forward and not derive the other two? You could derive the other two, just plug them into the integrated rate laws for zero order and first order.
Really easy.
But, go to the next slide. Second order half-life is calculated like this. It's going to be 1 over K times the initial concentration. And again, you could definitely derive this just by taking A equals 1/2 A0 and then solving for the time. And then zero order, A0 over 2K.
Is it true that each half-life in continuum will increase in time after the next one?
That's not true for first order.
Oh,
First order, the half-life is constant, it's fixed.
okay.
But for second order and zero order, the half-life is going to depend on what the initial concentration was. So the half-life is let's see, it's going up. For second order, the half-life is extending. Every consecutive half-life is getting longer and longer because you're starting with a smaller number here in the denominator.
Wait, so is A sub over the final absorption or the?
No, that's the initial concentration, yeah. Not absorption either, it's not absorbance, it's concentration, yeah, concentration of reactant. Yep. Honestly, gang, seriously, I do not memorize these. If I try to memorize these, my eyes would go crossed. I don't memorize stuff, and ln2 over k and then 1 over k. I can't remember that. I just derive it every time. I can remember the equations for the integrated rate laws, and I just set A equal to A0 over 2 and derive it. If you're good at memorizing, have at it. But don't be afraid to derive this thing if you just want to remember what the half-life means and what the integrated rate laws are for the orders, then that's good. So yeah, that's what I was saying here, a little note here. Half-life depends on what the initial concentration was for these two, 0 and second order, but it does not for first order. So first order, that half-life, doesn't matter how much you start with, it's the same all the time, if it's first order reaction. But the half-life really, I mean, you might, why do you need half-life? Half-life is a very clear indication of how fast the reaction is going. How fast does it take, or how long does it take, for your original concentration to get cut in half? That's an understandable way of knowing how fast the reaction is